In this video, we're going to study rational functions. Rational meaning ratio or fraction. They look like this. A couple examples we're going to jump into here in a second. In the first two objectives, you'll notice find the asymptotes and identify removable discontinuities. Those are both related to the domain. Okay, so I'm going to talk about these things as we go. And this will really define our function. It'll really tell us a lot about our function. What's happening with the asymptotes? We have vertical, horizontal, and slant. And these discontinuities that I'm going to talk about. Okay, but it all really starts in the denominator of the function. So if I look at that denominator, then I'm going to learn a lot. So before I do these examples here, let's just take a look at a couple functions just to get an idea. Okay, a couple graphed rational functions. So this is 1 over x. We've seen this one before with in our parent functions. So if you take a look at that guy, you'll see what's happening there at x equals 0, right? You'll notice the domain is everything but 0. X cannot be 0. And in this case, I have what's called a vertical asymptote at that bad point in the domain. That is, as I get really close to x equals 0, the graph has this crazy behavior, shoots up to infinity. As I get close to x equals 0 from the other side, it goes down to negative infinity. All right, so we're going to talk about that. That's called a vertical asymptote. And then we also have a horizontal asymptote. As x goes to infinity, y goes to 0, hugs that x-axis, where the y value is 0. As x goes back to negative infinity, same thing happens. Okay, so this is typical of these types of functions, this type of behavior with the asymptotes. And we'll see that mathematically when I look at the examples. So here's another one. This is 1 over x minus 1. It looks like the same thing as 1 over x shifted to the right. Now here's an interesting part. I'm going to graph x over x squared minus 1. And it's the same function, or it appears to be the same function. So we're going to take a look at what happens there. You'll notice the domain for 1 over x minus 1 is everything but 1. That would cause you to divide by 0. But in this function, x over x squared minus 1, if you factor that denominator, you would get a factor of x minus 1 and then a factor of x. So we'd have two issues in our domain here at 0 and at 1. So we're going to talk about what happens there. What else are we going to see? We'll see functions like this one that has actually x squared minus 1. That's what I wanted to do, sorry. X over x squared minus 1. This guy has two vertical asymptotes. Okay, and then so we'll study this function as well. But you'll notice the domain, it all starts with the domain. What's the domain of this function? X can't be 1 or negative 1. And then I have, in this case, two vertical asymptotes there. Okay, so that's an overview of the type of functions we're going to be looking at. Now let's jump into examples and approach these algebraically. What I'll do I'm going to say, here's a function, let's find out all the things. So the first thing I'll do for all of these is factor. Right? I need to know what the domain is. Maybe I should say that. The first thing I want to do is find the domain. How do we find the domain? We find the domain by factoring. So factor that numerator. I'll factor that denominator. And remember, for a domain, I'm just interested in for these problems in the denominator right now. That is, when is the denominator going to be equal to 0? Well, in this case, the denominator will be equal to 0, if I set each of these to 0, at x equals 0 and at x equals negative 1. Okay? So the question is, what's happening there? We got to decide what's happening for each of these. So the domain, I would write all x values as long as x does not equal negative 1 or 0. That's one way to write it. Or the other way, using interval notation, I go from negative infinity to negative 1. I skip negative 1 and I go from negative 1 to 0. I skip 0 and I go from 0 to infinity. Okay, same sets, different types of notation. So the real question we want to ask ourselves is, what happens at 0? What happens at negative 1? Okay, so I have, in this case, a like factor here. So x over x. So at x equals 0, I don't have a vertical asymptote. that is a bad point in the domain, but they're either going to be vertical asymptotes or they're going to be what's called a hole in the graph or a removable discontinuity. And I can explain why if you looked at what happens when I get close. So I have one of each here. So this is a vertical asymptote, and this is a hole. And I lead with this example because we're going to look at the difference in the two. So just imagine what happens as you get close to -1. Let's say I were to plug in negative 0.99. So I go 3, negative 0.99, that's close to 1. Negative 0.99 plus 2, that's close to 1. Negative 0.99. And then this is the key. When I plug in a negative 0.99 to this function and I add 1, these are just constants, so these are no big deal. Oh, sorry. These are no big deal. Nothing interesting here is happening. These would actually cancel out. This would be a number very close to 1, so no big deal there. This is the interesting part. That's 0.01. All right, when I divide by 1/100th, if I divide some number by 1/100th, it's the same thing as if you want to see it as a fraction, 1/100th. It's the same thing as multiplying that numerator by 100, right? In other words, dividing by a really small number is multiplying by a really big number. So that's where the vertical asymptote comes in. And if I get closer to 1, negative 0.999, let's say I plug that in. It wouldn't really matter for these guys. That would be closer to 1. That's just 3. This one gets even smaller, right? That's 0.001. And now I'm multiplying by 1,000. That's what gives me this behavior on the graph where it shoots up to infinity. You end up dividing by a really small number as you approach this bad value in the domain. And it either goes up to infinity or down to negative infinity. Okay, so that is my explanation for why this is a vertical asymptote. You get this behavior. Now, why isn't that happening at x equals 0? Well, if I did that whole explanation again, then what would happen with this function? I got 3 times, so I'm getting close to 0. So let's get really close to 0. 0.001. And then it was 0.001 plus 2. And then down here it's 0.001. I'm plugging it into this factored version. Easier to work with. 0.001 plus 1. Why don't I have the asymptotal behavior? Why doesn't it go crazy if I'm dividing by a really small number? I just told you if I divide by a really small number, like this isn't important. That's just close to 1. This is just close to 2. No big deal. This stays at 3. But I am dividing by 1/1000. So why is that not like multiplying by 1,000? Well, it's because these guys cancel out. It's because I have the like factors, right? That's really important. I have these like factors right here. So I don't have an asymptote. If there's a factor of x and a factor of x in the numerator and denominator, then you get this kind of cancellation behavior, so you will not have a vertical asymptote. Okay, so that's what I'm looking for. Let's go through these examples and just focus on vertical asymptotes. Then I'll come back and think about the horizontal asymptotes. So vertical asymptote, hole at x equals 0. If we actually want to find the hole, we can find the y value for where that hole is. So let me show you. This is my factored form of this function. And be careful, it's not really the same as, you're going to be tempted to just cancel out the x's. So let's do that and see what happens. Okay, if I were to cancel those, you want to say these are the same function, and they almost are the same function. They're the same function anywhere. The original function is the same function as this simplified function for every single value except at x equals 0. We got to be careful calling these the same. That's why I'm not using an equal sign here. I'm just using like a little arrow, because the domain of this one is everything but -1 and 0. And think about that. The domain of this one is just everything but -1. So they have different domains. Okay, which means they're not the same function. They are the same everywhere except x equals 0. But we can use this simplified version in order to find our hole. Okay, let me show you how that works. If I can get my pen back here. All right, so I plug in, I want to plug in f of 0, but I can't plug in f of 0 because I divide by 0. But I can call this a different function if I want. So I can, and then I can, because I don't want to call it f because it's not really f, but it's really close to f. And I can plug it into my simplified version, and that's how I'll get the output for the whole if I need to graph it. So that would be 3 times 2, which is 6, 6 over 1. And that's 6. So the hole happens at 0, 6. There's a hole in the graph there. Okay, let's see what I can do with example 2.